Welcome back to the Deep Dive. Today we're going beyond the simple chat interfaces we've all gotten used to with large language models.
They really are.
We're talking about turning an LLM into an entire autonomous research team. We're doing a deep dive into what are called deep research systems, or DR systems.
It's a huge leap.
Okay, so let's unpack that. I mean, we've all seen this crazy evolution. LLMs went from just generating text that sounded good to being, decent initial problem solvers.
Right.
But they always hit this wall, right?
You're right.
When you give them a really open-ended task, something that needs critical thinking, pulling from multiple sources, and this is the key, producing verified, cited answers.
A single prompt just won't cut it.
Exactly.
And that's really the gap that DR is designed to fill. It's not about a better prompt. It's a whole end-to-end research workflow.
A workflow.
Yeah, the agent doesn't just, answer a question. First, it has to plan the whole investigation, breaking the problem down. Then it goes out and acquires evidence using tools.
Like a search engine.
Like live search engines or even code executors. And then finally, it has to synthesize all of those verified insights into a coherent, long-form report, all with very little human supervision.
So it's the difference between asking a librarian for a book and asking them to go write a 10-page paper for you.
That's a perfect way to put it.
Okay, that brings up the big question. Everyone's heard of R, retrieval augmented generation. How is this different? Because that also retrieves information.
It does, but the core distinction is really flexibility and autonomy, especially over a long period of time.
What do you mean by that?
Well, a conventional RA system is kind of fixed. It's a static loop. It retrieves from a pre-indexed static database, and then it generates an answer. That's it.
And DR is?
DR is dynamic. It's adaptive. It can access live web APIs or run code when it decides it needs to. And crucially, it manages long horizon planning. It can work on a problem for hours or even days, constantly updating what it knows. RAG just isn't built for that.
So we're shifting from a static data lookup to a system that's basically running a full-on research project.
Exactly.
Our mission for this deep dive, then, is to explore the 4 foundational components that make this possible: query planning, information acquisition, memory management, and finally, answer generation.
And to really set the stage for that, it helps to think about this as a kind of capability roadmap. We see it happening in about 3 phases. Phase I is what we'd call agentic search. This is sort of the starting point. The main focus is just on finding the right sources, finding them fast, and pulling out concise, factual answers.
High recall, not a lot of deep synthesis.
Exactly. It's like a super-powered Q&A system. The truth is in one of a few documents, and its job is to find it.
And then we move beyond just finding facts. So that would be phase 2.
Right. Integrated research. This is pretty much the current frontier of what's being deployed. Here, the agent moves past isolated facts to produce these really coherent, structured reports.
And that's where the complexity must just explode.
It does, because now the agent has to handle conflicting evidence, deal with uncertainty, and pull together totally different kinds of data. Text, charts, tables. Think about things like market analysis or policy briefs.
And the final phase,
Yeah.
the really ambitious one.
That would be phase 3, the full-stack AI scientist. Here, the agent isn't just aggregating information anymore.
It's creating something new.
It's expected to generate novel hypotheses, run virtual experiments to validate them, and even propose new perspectives. We're talking about automating parts of scientific discovery.
That is a staggering roadmap. Okay, let's start at the beginning. Query planning, the very first step. The system gets a huge, complex question like, analyze geopolitical risks to rare earth mineral supply chains.
Right.
And it has to turn that into a structured step-by-step plan. This decomposition seems like it's everything. If you get the plan wrong, the whole project is doomed.
It is fundamental, and we generally see 3 main strategies for how they do this planning. The first is parallel planning.
Like the name suggests, doing things all at once.
Yep. It breaks the big query into a bunch of independent sub-questions and just tries to solve them all simultaneously. It's super efficient, very fast.
But what's the catch?
The catch is that it completely ignores how the sub-questions might depend on each other. It's a one-shot deal.
So if the answer to question A completely changes how you should have asked question B.
You've just wasted all the work you did on B. Exactly.
So that leads to the opposite approach.
Which is sequential planning. Here, it's iterative. Each new subquery is generated based on the proven answer from the step before it. It's context-aware, which is great for really deep, complex lines of reasoning.
But I can already see the problem. If you're building a chain and one link is weak,
The whole thing can fall apart. That's the critical
Right.
trade-off. It costs more computationally, and you have this huge risk of cumulative error. A small mistake in step 2 can become a catastrophic failure by step 6.
So how do you get the best of both worlds? The speed of parallel with the logic of sequential.
That's the goal of tree-based planning. This uses algorithms like Monte Carlo tree search or directed acyclic graph stacks. Think of it like a logical flowchart for the research.
So it's not a straight line, but it can't loop back on itself.
Exactly. No circular reasoning. It lets the agent explore different branching paths in the research, which gives you a really nice balance between speed and, effectiveness.
Okay, so the plan's in place. But a great plan is useless if you're feeding the system bad information. This brings us to the toolkit, or information acquisition.
Right. And the tools themselves have evolved so much. I mean, we started with lexical search, things like BM25, then semantic search. But now the real power comes from commercial web search APIs.
So just using Google or Bing?
Pretty much. You need that for real-time info, for scale, for freshness. Early systems like WebGPT showed just how critical this is.
But you mentioned earlier, for things like market reports, a lot of the key data isn't in a paragraph of text. It's in a chart or a table.
And that's the big push for multimodal retrieval. It's vital. When a DR agent finds a document with, say, a financial table, it doesn't just grab the text around it.
What does it do?
It preserves what we call grounded pointers. So the specific cell coordinates in that table or the exact boundaries of a chart. This makes the evidence truly verifiable. You can point to the exact spot the data came from.
That transparency is huge. Okay, let's talk about timing. You call it adaptive retrieval. This feels very human knowing when you don't know something and need to look it up.
It really is. The agent has to recognize the boundaries of its own knowledge. And it does this using confidence estimation.
How does it measure its own confidence?
There are a few ways. Not just the probability of the next word, but also consistency. It can generate a few answers and see if they all agree. If they don't, its confidence is low.
It's basically checking its own work.
Yeah.
And that low confidence score, that's the trigger.
That's the trigger. A system like self-RAG or React will literally generate a special token, something like retrieve, only when its internal signals say, hey, I'm not sure about this. This avoids searching for stuff it already knows, and it cuts down on noise.
Speaking of noise, querying the whole live web must bring back a ton of garbage. Filtering all that information has to be a major challenge.
Oh, it's absolutely essential. Bad documents can completely mislead the LLM, so filtering is about selecting, refining, and transforming that raw data.
Oh.
Well, there's document selection, where systems like RankGPT re-rank everything based on relevance. There's content compression, which distills huge documents down to just the key points. And then there's simple but crucial stuff like rule-based cleaning.
Like stripping out all the HTML junk from a web page.
Exactly, getting rid of ads, navigation bars, all that boilerplate so the agent can focus on the actual content.
All this complexity really shows that the LLM is more of an orchestrator, a brain managing a team of specialized tools.
And that orchestration is never more complex than in memory management. This, I think, is what truly separates a DR agent from a simple RG system. It's the ability to maintain a coherent context over a really long task.
So let's walk through that life cycle.
Mm.
It has to start with just taking all this raw input and making it storable, right?
That's the first step, memory consolidation. It's about turning those transient, short-term experiences, a tool's output, a draft of a sentence, into a stable long-term memory.
And what does that look like?
It can be unstructured memory, which is basically just distilling a long history down into a high-level summary. Or, more powerfully, structured memory, where it organizes data into things like knowledge graphs.
An actual graph.
Yeah, a system like HippoRag builds a web of interconnected facts with explicit relationships that's way more durable and useful than just a paragraph of text.
Okay, so you've stored the memory.
Yeah.
How do you find what you need later without getting lost in this huge growing history?
That's memory indexing, building a smart navigational map. And it's way beyond just keywords. We're seeing things like signal-enhanced indexing, where you add metadata, like how credible the source was.
Or when the memory was stored.
And even better, when that fact was valid in the real world. A system called ZEP uses what's known as a bitemporal model. It tracks both. For financial data, that's absolutely crucial. A fact from last year might be actively harmful today.
But knowledge changes. New information comes out that contradicts old information. How does the agent update its own beliefs?
That's memory updating. This can happen externally, we call it non-parametric, using explicit commands like ADD or update, or an agent can use self-reflection to correct its own reasoning.
And internally.
That's parametric updating, which means changing the model's actual weights. This used to be incredibly expensive. But now we have techniques like modular updating.
A module?
Yeah, you compile new knowledge into a dedicated, lightweight, sort of plug-and-play module.
Like a topic-specific flash drive for the model's brain.
That's a perfect analogy. It avoids this huge problem called catastrophic forgetting, where learning one new thing makes the model forget 50 old things.
And what about just forgetting things on purpose?
Memory forgetting. It's not a bug, it's a feature. It's a functional, necessary process to get rid of outdated or irrelevant stuff. It can be passive, just letting old memories decay over time, like a FIFO queue.
Or it can be active.
Right, active forgetting. This is intentional removal, may be triggered when the agent finds a direct contradiction. Some systems literally use a delete command. It's about keeping the memory clean and relevant.
That entire life cycle, consolidation, indexing, updating, and forgetting, that's what gives it the consistency to work for days on a problem.
Absolutely. And that brings us to the final component, answer generation. This is where it all comes together. It's not just spitting out text, it's creating verifiable, presentation-ready knowledge.
I think the biggest challenge here has to be when sources conflict. If one study says yes and another says no, how does the agent decide who to trust?
A human would check the source, right? A peer-reviewed journal is worth more than a random blog. So these systems now use credibility-aware attention. They weigh evidence based on the authority of the source.
Okay, that makes sense.
They also use more complex methods like multi-agent deliberation. You basically simulate a committee of experts.
So you have different agents arguing with each other.
In a sense, yeah. Different agents analyze the documents from different angles, and then a meta-reasoner synthesizes a nuanced consensus from their debate. It's much more robust than just averaging the results.
And how do you force it to be factual? To not just make stuff up to sound good?
That's where reinforcement learning for factuality comes in. Systems like RioRag get a reward when their claims are supported by the evidence they found, and they get penalized if they generate unsubstantiated claims. It trains the model to value truth over fluency.
And for that final report to be useful, you have to be able to follow the logic. The reasoning needs to be transparent.
Completely. And we've moved past simple chain of thought prompts. Now we're seeing explicit structural planning where the system first designs a detailed outline or a DAG for the answer before it writes a single word.
So it's designing the argument first.
It is. It's designing a presentation, not just writing a paper. And that's the ultimate frontier here, presentation generation. The answers aren't just text anymore. They integrate visuals, tables. Some systems can generate an entire fully editable slide deck as the final output.
That's incredible. So you have these unbelievably complex systems running, planning, using tools, managing memory. It must be so computationally expensive. How do people actually make these things work efficiently?
Yeah, that's key. It really comes down to three main ways they optimize them.
Okay.
The first is workflow prompt engineering. This is where you build a kind of multi-agent team. Anthropic's deep research system does this. There's a lead orchestrator agent, the manager who delegates tasks to specialized worker agent.
And the manager keeps them on budget.
Exactly. It follows an explicit research budget for how many tools can be used or how many agents can be spun up. It prevents things from getting out of control.
What's the second method?
That would be supervised fine-tuning, or SFT. This is how you give an agent its basic skills. But getting the training data for these complex tasks is hard, so they often use something called strong-to-weak distillation.
That sounds like a master chef teaching an apprentice.
That's a great way to think about it. You took a huge expensive model like a GPT-5 and you record its entire decision process, the plan, the searches, everything. Then you use that data to train a smaller, cheaper model to mimic it.
And the third and final optimization method.
That's the most advanced, end-to-end agentic reinforcement learning. This uses algorithms like PPO to reward the agent based on the quality of its final answer. It optimizes the whole workflow, planning, acting, generating all at once to get the best possible outcome.
So when you put it all together, what does this actually mean for all of us? It seems like DR systems are taking LLMs from being simple chatbots to being truly autonomous research teams.
That's the takeaway. They can manage massive amounts of data, maintain a complex memory, and plan over long horizons. They're automating the full iterative cycle of human research.
The integrated memory and the adaptive tool use. That's what lets them tackle these huge, complex tasks that were just impossible before.
Right. From deep market analysis all the way to things that start to look a lot like scientific peer review, the coherence and verifiability are on a whole different level.
It's a massive leap.
Mhm.
But it also creates a really fascinating, almost philosophical problem for us, the users, especially as we head towards that phase 3 you mentioned. One of the biggest challenges in evaluating these systems has to be defining the line between true novelty, a genuinely new and valuable insight, and just a sophisticated hallucination. As these agents start proposing new ideas, how can we, the humans in the loop, reliably tell the difference? That's definitely something to mull over until our next deep dive.